Hi, I'm going to go through this paper, Zero Knowledge Signaling on Ethereum, to better understand how it can provide privacy solutions on a layer 2. At the core of this solution is a Merkle tree inclusion proof. So we have a public Merkle tree that we can insert hashes to and then prove that we have a hash that makes up the Merkle tree root. So to prove that our leaf of the Merkle tree makes up the Merkle tree root, we just need to collect some public hashes. So we collect this hash and then we calculate the hash on the layer above, and then we collect this hash and then we calculate the Merkle tree root, which can let us prove that our leaf is inside the Merkle tree structure. One other data structure is something called a nullifier map. And that is basically keeping track of whether or not a signal has been used before. And finally, we have a signals map, which will just map the signals to the hashes. So here we have a Merkle tree. Let me just go through the specifications. A Merkle tree is a binary tree. Every leaf needs to be filled out. If the bottom leaves do not fill the whole span, you just repeat the leaves. The hash for the next level of branches is calculated from left to right. We hash these two leaves in this order, so left then right, to get us this value. So with a smart contract, we deal with a flattened Merkle tree, which is basically each layer of leaves, one after the other. Here we've got the bottom layer of leaves, then we have the next layer of leaves, and then we have the layer just below the Merkle root. To do an inclusion proof, all we need to do is collect up the hashes that we need as we traverse the Merkle tree. So to prove that this leaf helps make up this Merkle tree root, we need this hash, and then together with our leaf we can calculate this hash, and then with this hash, with our calculated one, we can calculate this hash, and then with this hash we can calculate the Merkle tree root. So as I mentioned, one of the specifications is that you hash left to right, which means we need to keep track whether or not the hash that we are using is on the left of the branch or on the right of the branch. Let's now look at the actual hashes that will get put into the Merkle tree. So in the paper, in the appendix, they link to some GitHubs, and there is a GitHub for an actual implementation of what is proposed in the paper. So here I've cloned that. If we go into the packages and then go down to identity, we can look at what is actually going to be put into the Merkle tree. So we have a message or an identity, and we do a SHA-512 on it, and then the code is splitting that hash up into two parts, and then it's doing a Poseidon hash on it, and then it's doing another Poseidon hash. Here I've got my message. Hello, this is a message, and this long number here is my SHA-512. From that we create these two numbers. One in the paper is referred to the trapdoor, and the other is referred to the nullifier. This is referred to the nullifier because it is part of what makes up the hash used in the nullifier map. And then from these two numbers, we create our actual commitment hash, which goes in the tree. Let's now look at the proof, which is the core of the system. So if I go to circuits, then we have a semaphore.circum. So the semaphore is our main component in our entry, and we have two public input signals, the signal hash and the external nullifier hash. The external nullifier is just a locally computed hash, which then is used in our nullifier map. So here's our semaphore template circuit. So we've got our input signals, we've got the identifier nullifier and the identity trapdoor, which, as we recall, come from our hashed message. Then we have the tree indices and the tree siblings. So these are the public hashes of the Merkle tree, which we need to compute the Merkle tree root. Then we have the external nullifier. Then we have the output signals, the root and the nullifier hash, which is the actual hash in the nullifier map, and that's merely made up by hashing this and this. And it's done like that so that you can broadcast the same signal each time. You just need a unique locally generated hash. So first of all, we are making an instance of the calculate secret, and the calculate secret takes our identity nullifier and identity trapdoor. And all this template is doing is this step here. Then we have a calculate nullifier hash, and this component takes in the external nullifier and the identity nullifier. And again, all it's doing is a Poseidon hash, and that output will be what is in our nullifier map. So next we have the calculate identity commitment component, which takes the secret calculate commitment. So that is just a Poseidon hash with one input, which again is just recreating what we to create our identity. So it's this step here. And then we move on to the inclusion proof. The crux of this system is the Merkle tree inclusion proof, which I'm going to recreate here to show the different steps involved. So with the documentation, let's create a circuit. To do our proof, we will need an input signal of the leaf, an input signal of the other leaves that we will need, the indexes of the other leaves that will be used in calculating the root. And then for the output, we will have the root. And the tree is height of 4. The only public signal is the leaf. So first of all, we are going to want our hashing function. So what you will want to do is install this circumlib package, npm install circumlib, and that will give you access to library circuits. Here we've got circuits that we can use. We're going to want to use the Poseidon hash. So let's look at this circuit to see how we use it. Okay, so we specify the number of inputs. So we pass it the hashes, and then we get the output. For each layer of the tree, we have to calculate the hash on the next layer. So we will need a for loop, and we will need a structure to store the calculated hashes. One other consideration is the ordering of the hashes. So if our index is even, then that hash goes first, or if our index is odd, that hash goes last. So there is a gates function, and we can use the AND. We are going to need as many components as there are layers on the tree, because we have to perform a hash for each layer of the tree until we get to the root. So we will create an array of components, and there's one more component we're going to use, because we need to switch the position of our inputs to the hash function. So first we need to work out if the hash needs to go first or second. We can do that by doing an AND. So 5 and 1 is 1, meaning it's odd. We will need to seed our leaf, and then we're going to use this mux function to look at the documentation. So here to this mux component, we've passed 2 hashes in both configurations, and now we need to select which situation we need. If S is 0, we are going to get the components in this order. So next we need to do the hash inputs. We add the output of the hash to this array ready for the next round. And then lastly, we assign the output signal. Okay. Everything went okay, circumsafe. So, zero knowledge signaling on Ethereum lets you signal an intent with one address, and then at a later date enact that intent with another address, which brings us on to the topic of relayers. What is a relayer? When you do a transaction on Ethereum, you have to pay gas, as you are basically asking participants in the network to do work. And by paying gas, you potentially undermine the whole purpose of the zero knowledge signaling on Ethereum, as the gas can be tracked back to somewhere with KYC, which can then de-anonymize yourself. A relay is basically a service that sends your transaction for you and pays the gas for you. So the person paying the funds is whoever's running the relayer and not the owner of the clean address. Now, we cannot talk about relayers without mentioning Tornado Cash. So Tornado Cash is the most well-known application built on top of zero knowledge signaling on Ethereum. It is a mixer, and they recently got fined by this organization. The charge placed against them was that they had materially assisted, sponsored, or provided financial material or
technological support for, or goods or services to, or in support of a cyber-enabled activity originating from or directed by persons located in whole or in substantial part outside the United States that is reasonably likely to result in or has materially contributed to a significant threat to the national security. Blah-de-blah-de-blah. They didn't like what they were doing. That implies they profited from. And that is because people who run relay layers get a little bit of payment for providing the service. So in conclusion, zero-knowledge signaling on Ethereum is an ingenious mechanism on top of which useful anonymous applications can be built. However, the case with Tornado Cash makes clear that there is a need for an anonymous by default layer 1 network on which smart contracts can exist.